Welcome to the second day of RMIT Conference 2017. It is my honor to introduce Professor R. Balasubramanian. He is one of the most prominent mathematicians of the current times, and I must mention his many achievements so as to inspire us all. Professor Subramanian did his PhD from TIFR Bombay and was a faculty of maths in Institute of Mathematical Sciences, Chennai till recently. He also held the director position for a long period. He had received many awards. Some of them are Young Scientist Award, INSA, Young Associate of Indian Academy of Sciences, B.M. Birla Award, S.S. Bhatnagar Award, Srinivas Ramanujan Birth Centenary Award of Indian Science Congress. Also Fellow of American Mathematical Society in 2012. He also awarded with the Lifetime Achievement Award in 2013 by Manmohan Singh. He also got the Padma Shri Award in 2006. Presently, he is an INSA research professor in Institute of Mathematical Sciences, Chennai, and also the head of National Center of Mathematics at IIT Bombay. One more thing I would like to add, what sir told us is that he is pleased to have Professor Manisha Kulkarni as his PhD student. Professor Subramanian is also known for his stellar work in the field of analytical number theory. So today he'll be speaking about the factorization of integers. So I request Professor Subramanian to start his lecture.
The factorization which I was planning to talk is some sort of a multiplicative analog of partitions, and therefore let me first of all say a little about the partitions and then I come to the factorizations later. This is the type of questions which you people would have seen. How many ways an integer n can be written as x plus y plus z with x, y, z greater than or equal to 0. And is there a closed formula for it? How many ways I can write a given integer as a sum of 3 numbers, and is there a closed formula for it? And the answer is yes. You can actually write a closed formula for this. And one way is probably to approach combinatorially, and then you can somehow guess a few guesses of what the closed formula should be. And once you made the guess, then probably you can use it by induction, because you do it for n and then you can do it for n plus 1. But one of the convenience way to do such problems is, first of all, as I was telling, the combinatorial way, first of all you have to make a guess and then you put by induction. And therefore one of the convenient ways to do this problem is to use the so-called generating functions. Okay, and that would, okay, therefore let me explain what the generating functions are. And suppose you have a sequence an, and you want to study this sequence an, and one of the nice ways is essentially to look at this following function. And then study the properties of this function, summation a n x power n, and once you have studied the properties, from that you can deduce something about the a n. Okay? Therefore, let me first of all give, not connected with this, let me give a simple example of what one can do with the generating functions. And one of the easiest things where what one can do with the generating functions is essentially to study the Fibonacci sequence. This is the function f of n plus 1 is equal to fn plus fn minus 1, and this is a function which most of you would have studied, and most of you would be interested in knowing how fast this function grows. What would be, I mean, whether it grows like a polynomial, whether it grows like an exponential, what is, how far it grows. Have any of you seen that, how far it goes? What is the rate of growth of fn? And unfortunately such problems of course cannot be even proved by induction, I mean, because you don't have an exact formula. You know, if you only have a rough formula, then it becomes more difficult. Okay? Therefore, let us try to do how the generating function will help us. Therefore, let us do the generating function business. Therefore, I have an fn x power n equal to 0 to infinity. Okay, and now let me do the following thing. Let me multiply by 1 minus x square. If I do the 1 minus x minus x square, and now for m bigger than or equal to 2, let me look at the coefficient of x power m. What will be the coefficient of x power m when I look at summation fn x power n multiplied by 1 minus x square? There will be a term fm x power m here, and fm x power m multiplied by 1 will give you a one coefficient of x power m, and therefore that will give you fm. There will be a term which is fm minus 1 x power m minus 1. This fm minus 1 x power m minus 1 multiplied by this x will give you fm minus 1. And there will be a term like fn minus 2 x power n minus 2 multiplied by this x square, that will give you fn minus 2. Correct? Therefore, the coefficient of x power m would be fm minus 1 minus fm minus 2, and by assumption this is equal to 0, because that is what is given to you. That is the definition of Fibonacci sequence. Okay, which means that you take this generating function summation fn x power n and multiply by 1 minus x square, then every coefficient greater than or equal to 2 vanishes. Only the first two coefficients probably will survive, and therefore this is precisely is equal to, there will be a coefficient f naught multiplied by this, and then the coefficient of this is a constant term, and the x term would be, there will be an f1x into 1, and then there will be a f0 times this. Therefore, what you get essentially is that summation fn x power n to 1 minus x square is just a linear polynomial, a polynomial of two terms, and in fact by our assumption this is precisely equal to 1, because I am assuming f naught equal to 1 and fn minus 1. What does it mean? That means essentially that you have a sigma fn x power n is equal to 1 minus x square. Therefore, you have now been able to write the generating function in a much better way. That is a rational function with a denominator of degree 2. Okay? Does it really help us to know how fn grows? No. Our whole problem is that we want to know how fn grows. But now I have only proved that summation fn x power n is equal to 1 minus x square. Can you see any way of really seeing how fn grows from this? I mean, in other words, can you write the expansion for 1 minus 1 over x minus x square? If you can write the expansion, then you are through. And how will you normally write that? If you want the expansion of 1 minus 1 minus x square, how will you do that? Sorry? If it is a linear polynomial, it will be geometric, which is a quadratic. But you know, on the other hand, I will say you are 50% right. Somehow the quadratic should be made into linear and then do that. How do you make the linear? You have already said how to write this partial fractions, no? I mean, because you can now factorize this 1 minus x square. And what are the roots of this? Let us write as x square plus x minus 1 equal to 0 by the standard things, and it is equal to minus 1 plus or minus square root of b square minus 4ac by 2a, which is equal to minus 1 plus or minus square root of 5 over 2. Call this number alpha, and therefore essentially what you have is 1 minus alpha x into 1 minus alpha x square, alpha bar x. Okay, which all of you know can be written as a by 1 minus alpha x plus b by 1 minus alpha bar x. For an appropriate a and b, and all of you would have studied even how to compute the a and b.
Bar is not complex conjugate.
Oh, bar is not, okay, yeah. Bar is not complex conjugate. So, minus 1 plus root 5 by 2 and minus 1 minus root 5 by 2. And once you have this, now you can use a binomial theorem. and therefore this is nothing but A into summation alpha x power n plus summation alpha bar x power n. And therefore Fn, which is the nth coefficient of this generating function, the nth coefficient Fn of the generating function is precisely A times alpha power n plus B times alpha bar power n, where you can, if you want, you can sit down and compute what is value of alpha and what is A, what is B, etc. You know how to compute it. You know how to compute A and B. Therefore A and B you can compute. You know the alpha also. Alpha is root 5 minus 1 by 2, and another is minus of root 5 minus root 2, and then you can do this. Okay. Therefore we have found out the exact value for Fn. Okay. And that is can be done essentially by using the generating function. And now let us go back to my problem. My problem is now to write n as the sum of x plus y plus z. Where do I have this? Okay. Therefore, let Fn be the number of elements of this. Therefore, Fn be the number of solution of n is equal to x plus y plus z, and then I want to know whether somehow I can write Fn into x power n, this generating function, and whether I can write it in a nice way. And once I can write this generating function summation Fn into x power n in a nice way, then of course I have a formula for Fn. How many ways n can be written as sum of 3 integers. Okay, let us do that. Let us do the following. Let's take this power series 1 plus x square plus x cube plus etc. x power a, and I think all of you would recognize what this power series is. What is this? 1 by 1 minus x, and take the another power series and take another power series and multiply the 3 power series. Multiply the 3 power series, and then I am interested in knowing what is the coefficient of x power n. Therefore, I take the first power series 1 plus x square plus etc. x power a plus etc. Another power series 1 plus x square plus x power b etc. and another power series 1 plus x square plus x power c etc. I want to multiply all the 3 and know what is the coefficient of x power n. How will I get it? I take one typical term here, one typical term here, one typical term here, multiply in such a way that I get x power n, and I keep on doing it for all possibilities and then add them. That is all the coefficient of x power n. Okay. Therefore, I take one typical term x power a here, one typical term x power b here, one typical term x power c here, and multiply. That will be x power a plus b plus c. Therefore, I should choose a, b, c in such a way that a plus b plus c equal to n. Okay. Therefore, all possible ways of choosing a here, b here, c here, such that a plus b plus c equal to n. If I do that and keep on multiplying, and every time I do that, I will get a x power n. Good. That means by definition the coefficient is Fn, because that is how I have defined my Fn. I have defined my Fn to be the number of ways n can be written as sum of 3 integers. Okay. Since I have defined my Fn to be the number of ways I get sum of 3 integers, it follows that if I take one of them here, one of them here, and multiply in such a way that I choose a plus b plus c equal to n, I will get that. Okay, that means already I know what this thing is. Because this is precisely Fn x power n, and this is Fn x power n, and but this is of course 1 minus x inverse, this is also 1 minus x inverse, this is also 1 minus x inverse. Therefore, I multiply these 3 and get my summation Fn x power n, and therefore this is precisely 1 minus x power minus 3. And then for all of you know how to expand the 1 minus x power minus 3 by binomial theorem, and then you know what the coefficient is. And what is the coefficient? How will this go? How is the expansion of 1 minus x power minus 3? It goes like what? 1 plus 3x plus 3 into 4 by 1 into 2 x square plus 3 into 4 into 5 by 1 into 2 to 3 x cube, etc. Correct? And what is the coefficient of x power n there? Good. I will give the answer and then I will leave you to check. F of n is precisely n plus 2 choose C. And therefore, you know the coefficient of Fn is n plus 2 by 3. Therefore, the number of ways of writing n as a sum of 3 integers is precisely has a closed formula. Good. Now let me make the problem a little difficult.
Choose 3.
Sorry?
N plus 2 choose 2 or choose 3.
N plus 2 choose 2, is it? Let's see. 1 and then a 3 and 3 plus 4 by 2, 3, 4, 5 by 1, 2, 3. These 3 will go away, correct? Yeah, therefore it has to be quadratic in n. Yeah. Because there are only 2 independent variables. N plus 2 choose 2. Okay? This is xyz greater than or equal to 0. Now I want to generalize a problem, and that's where we get into problem to start with. Okay, I want to make the problem a little slightly different. I will make x plus y, xyz equal to greater than or equal to 1 for technical reasons which I will explain in a minute. Therefore, I have written n as a sum of 3 integers. Okay, and I also would like to say yeah, and what I want to say is essentially therefore up to permutation. Okay, therefore, okay, I don't consider 5 plus 3 plus 1 to be different from 5 plus 1 plus 3. Okay, therefore it's only the pairs. Which is one of the easiest way to essentially do that is to make this assumption. If I make this assumption x is bigger than or equal to y, bigger than or equal to z, then this question of 513 and 531 both being considered will never arise, because you have already arranged an order. Okay, therefore we will make those assumptions. The assumption is that therefore an ordering is already fixed, the decreasing ordering, and all the summons are bigger than or equal to 1. The reason why I want to do that is that if you want to call this thing as f3 of n, the number of ways of writing n as a sum of 3 integers, and I am now more interested in the following function. Therefore, I want to write this n as a sum of 1 integer, sum of 2 integers, and a possible way sum of 3 integers, sum of 4 integers, everything, and that number is what is called the partition function. Okay? And now let me explain the reasons why I made those changes. If I have not put xyz greater than or equal to 1, if I had put xyz greater than or equal to 0, okay, then for every n there will be at least one representation. And if there is going to be at least one representation, this infinite sum will be infinity. Therefore, there is nothing which you can do. Whereas now by this doing, I have made this, the sum will not go up to infinity. If n equal to 15, for example, there is no f16n. There is no way the n equal to 15 can be written as sum of 16 elements, all of them greater than or equal to 1. Therefore, f16, f17, everything will vanish. Okay, therefore, it will be a finite sum. But on the other hand, if I don't put that condition, of course, still there will be an f16n. 15 can be written as sum of 16 elements, some of them being 0. Therefore, the 0 I cannot allow. Okay, this is what is called the partition function. Therefore, the partition function, which was studied by Ramanujan, one of the important things studied by Ramanujan, is essentially the number of ways of writing n as sum of integers up to permutation, because I have fixed the order, and the number of summands is varying, but all the summands should be greater than or equal to 1. Okay. This is the function. Of course, this is not the function which we are going to study. After studying this function, what we are going to study is the multiplicative analog of that function, which is the factorization. Here, because you are writing n equal to x plus y plus z, what we want to study is n equal to x into y into z. It's a similar question, but anyway, we will come to that later. I don't think I will have even time to come to that. But anyway, this is what it is. It will be finite, no? It will be finite. It will be finite, yeah, because, yeah, okay, because there cannot be more than n summands anyway. If you are given a fixed n, for a fixed n, I mean, because all the summands are bigger than or equal to 1, and therefore that stops. And the first person who studied this question is Euler, and Euler studied these questions both by combinatorial method, and by generating function method. Therefore, let me just give you a couple of examples of what Euler did, both by combinatorial method and the generating function, and then I will say that Ramanujan was interested in a completely different type of question. Okay, therefore, what did Euler prove? Okay, therefore, let me check. One of the theorems which Euler proved, let me first of all even give a proof and then probably we can. Suppose I take this partition. Therefore, I am now looking at the partitions of 7. Okay, this partition of 7, let us take one partition. Okay, therefore, let me give you an example. Sorry. Therefore, 5 equal to 5. This is F1 of 5. This is F2 of 5. You should realize there are precisely 2 ways you can write 5 as a sum of things distinct in the decreasing order. 4 and 1, 3 and 2, and there is no other way. And this is the only way, 2 ways. And that's the only way which you can write 4 as a sum of 5 as a sum of 4 elements. And this is the only way which 5 can be written as a sum of 5 elements, and then everything else will become 0. Therefore, Fi of equal to 7. You can just write all those things individually. Is it okay? And now let us look at this particular partition 7 equal to 4 plus 2 plus 1. Therefore, we can just make it as a graph. And the row wise, when you read it, it is 4 and then the 2 and then the 1. Okay? But then this, you can read it as column, and therefore this gives another partition. Correct? I have only the same diagram. This diagram I can read row by row, and then I get 4 plus 2 plus 1, and I can read column by column, and then I will get 3 plus 2 plus 1 plus 1. Correct? And now what happens is, when you write row by row as 4 plus 2 plus 1, the maximum summand here, which is 4, that is a maximum summand, actually becomes here the number of summands. That is essentially because that is what I have done. I mean, essentially whatever, therefore the maximum is what will be in the first row, and these rows don't matter. Therefore that maximum, but when you now read column by column, the number of summands will be precisely equal to that. Therefore the maximum summand has becomes the number of summands, therefore there is a bijection. Therefore given one, okay, that essentially means already we have proved the following theorem: the number of partitions with all summands less than or equal to m equal to number of partitions with the number of summands less than or equal to n. Therefore, the number of summands and maximum summand is essentially, you can write the first one, all partitions with all summands less than or equal to m, and then take the conjugate partition and conversely. Okay? Therefore, there is something which we have proved a theorem just by drawing a picture and nothing more than that. This picture already proves that this is exactly what happens. Therefore, you can do it combinatorially, but you can also do many questions again by generating function. Okay? When I wanted to write something as a generating function, then what happens is I wrote here for that question was 1 minus x power minus 3. Okay? And therefore, now this question now is that the number of partitions would be what, x power n or n here, where x power, where should you put it, minus n. Oh, sorry, I got. Okay, let us see what happens. Therefore, you now look at, no, the other way.
Okay.
Yeah, you look at this 1 plus x square plus x cube plus etc. and then 1 plus x square plus x power, sorry, let me not write like that. Yeah, let me write like that. The first number is 1 minus x inverse, the second number is 1 minus x square inverse, the third number is 1 minus x cube inverse, etc. Okay? And now let us look at the coefficient of x power n, 7. Okay? X power 7, I have to take one term and one term here, so that the product will give you 7. For example, I can take this term and this term. That will give you the partition which is 3 plus 2 plus 2. Okay. And that is the reason why I did not write the 4 here, because then it will be difficult to see that 4 is actually standing for 2 plus 2. But if you write like that, I mean that's clearly, and therefore if 7, if you want really 1 plus x power 4 plus x power 4 plus 4 etc. And then I can take x power 4 here and x power 1 plus 1 here, and that will correspond to this partition. Okay? Therefore, I can take one term here, various brackets and add 7. And then you can clearly see that this is precisely the number of partitions of 7. Okay? Therefore, I know the generating function of product 1 minus x power n inverse, because that is my Pn. Okay? With that, using the generating function, we are going to prove a theorem, which is again. Therefore, let me write the generating function, and therefore the generating function is this. Okay? This let me write slightly differently. 1 by 1 minus x is nothing but 1 minus x square by 1 plus x. and this is 1 minus x power 4 by 1 plus x square, and then when I have so other way. This is all. Oh, no, that won't even cancel. Yeah, odd and even is what I want. And how do I get the odd and even? 1 minus x square, then I write 1 plus x by 1 minus x square, then what will I get? Yeah, this is 1 minus x, which won't give you what I want. Really, I want really the confusion. Okay. The number of ways of writing, the number of distinct partitions is equal to exactly. Okay. Let's write. Now look at this following. Okay. When I now look at this sum, then I am going to take different elements from different brackets and I am going to multiply. Okay. The main difference between the previous case and this case is that whatever terms which I am taking from different brackets, their powers will be distinct. Correct? Okay, that's the only difference essentially. Therefore, this will actually give you the number of partitions where the summands are actually distinct. So this gives you the number of partitions with the distinct summands. Okay, this is a generating function. Now let me simplify this generating function. Therefore, the 1 plus x I have written as 1 minus x square by 1 minus x, 1 plus 1 minus x power 4 by 1 minus x square, etc. Now this numerator cancels. This numerator cancels. And then this numerator, the next numerator cancels. Then you see all the numerators will get cancelled. What will remain is only the denominators. The denominators is again of the form 1 minus x power something, where that something is an odd number. Correct? And therefore, what you are having is essentially 1 minus x into 1 minus x cubed into 1 minus x power 5 inverse. And what does it stand for? Any guess? Because you know what 1 minus x, 1 minus x square, 1 minus x cubed, etc. stands for. That stands for the number of partitions. Then what will the 1 minus x, 1 minus x cubed, 1 minus x power 5, etc. will stand for? What is the part that will stand for? When you expand it, what will you get? All the summands would be odd. 1 minus x, okay, because now when you expand it and you write the way which we wrote earlier, if you expand like that, and then when you look at what does this stand for, this really stands for the number of partitions into the odd summands. Therefore, that is exactly the theorem which Euler proved, that the number of partitions with the distinct summands is the same as the number of partitions with the odd summands. And this cannot be proved by using all those graphs. You need a generating function. Good? But the question which Ramanujan was interested is the generalization of the earlier question which we asked. The question which we asked there was how many ways n can be written as sum of 3 integers and you have a closed formula. And what he was interested in knowing whether the partition function has a closed formula, and if so, what is it? How fast it grows. Okay. Now this is a natural question. I mean, because that's the question which we started with n equal to x plus y plus z, and then we are interested in knowing whether it can be extended. Yeah. And that's exactly the things which I want. Okay. And one knows now that there is really no closed formula for the partition function, but you can get an asymptotic formula because this function grows very fast. Okay. And Hardy and Ramanujam actually proved that that's the last line of the things, that there is a formula which is therefore the number of partitions of n is 1 over 4n times the square root of 3 into around exponential pi times the square root of 2n by 3. That's a formula they proved by using circle method. Okay. And in fact, the genesis of this is actually there in the very first letter which Ramanujam wrote to Hardy. And in that particular letter, he is not talking about this formula. Okay, therefore now let us see what is that thing. Okay, what is this Pn? We have seen what this Pn is. This Pn is take 1 minus x, 1 minus x square, 1 minus x cube, etc. and take that and then take the inverse, and then you want to know the coefficients. And this is a power series with bounded coefficients. And in fact, I think it was even already proved by Euler that if the number is of the form 3n plus or minus 1, the coefficient will be 1 and otherwise it is 0. Therefore, the coefficients are either 0 or 1 depending upon what the structure is. Okay. Therefore, what you are now looking at is a naturally occurring power series with the coefficient 0 or 1. And then you are taking the inverse. And with so many examples now, it looks that for a naturally occurring power series with the coefficients which are 0 or 1, and if you take the inverse and you take the coefficients grow exponentially. Okay. Therefore, the original function has only 0 or 1, but you take the inverse and then that seems to grow essentially exponentially. And here you can see that it goes exponentially right to pi n. And the question which Ramanujam originally wrote was the so-called theta function. He took the theta function, which is by definition summation minus 1 power n x power n square, n equal to 1 to infinity, and then he says that you take this function which has a coefficient 0 or 1 and take the inverse of that, and then what is the coefficient of x power n, and he proves that it grows exponentially, and that occurs in the I think the formula number 1.14 or something like that in the very first letter of Ramanujam to Hardy. And then of course, then Hardy wanted to know how he proved that result, and then which Ramanujam explained how the development of the so-called circle method using which they proved it. Okay. Now the question which I am interested, I think I have already taken the introduction itself. The question which we are interested is the multiplicative analog of this question. The multiplicative analog of the question is therefore now instead of writing n as a sum of 3 elements, I am going to write n as a factorization of 3 elements. Exactly. Therefore, this is the question which we are interested in. Let Fn denote the number of unordered factorization of n into factors larger than 1. As I said that last time I could not allow 0, this time I cannot allow 1, because if I allow 1 then the number of partitions will be infinity. Only again unordered for the same reason which I explained. I mean, that's really, you can always assume that it is a decreasing order. And more precisely, Fn is the number of tuples such that 1 less than n less than or equal to n1, n2 less than or equal to nr, such that n equal to n1 into etc. nr. For example, f of 18 equal to 4, because 18 can be written as 18, 2 times 9, 3 times 6, 2, 3, 3, and this is the only way it could be written. And therefore, this is in some sense the multiplicative analog of the additive problem of partitions. And we would like to study this. Okay, what is it we want to study? The question is, what is the order of Fn? The order of Fn was already done by Oppenheim, and he proved that the average order of if you sum of the value of Fn and sum it up, it is x into exponential 2 times square root of log x by 2 square root of pi log x power 3/4. Therefore, proving more or less roughly that every Fn is something like an e power 2 times square root log n. That is the average order of Fn. Okay. And then further investigation done by Canfield, Yerdash and Pomerance, and they were interested in the maximum order of Fn. The maximum order of Fn they proved is, you see, the average order is exponential 2 times square root log n, but the maximum order is essentially bigger than n power 1 minus epsilon. Therefore, in spite of the average order being so small, exponential 2 times square root of log n, therefore the maximum can be as big as n power 1 minus epsilon. Okay. Now the question which I am interested is whether the values taken by Fn is a dense set or a rare set. Okay. Therefore, I compute Fn for each value of n. Okay. After computing Fn for each value of n, how many values Fn takes? Because the Fn will take the same value at too many n's. Okay. For example, if you look at f of p is the number of ways of writing p as a product of primes 1. Therefore, for every p it will be f of p equal to 1. Therefore, the f seems to take the same value, same value lot of times for all the primes f p equal to 1, etc. And therefore, the question is that Fn takes the values rather rarely, because it seems to take the same value again and again and again. And therefore, that Canfield, Yerdash and Pomerance made the following statement: we are able to show that the number of values that do not exceed x is x power little o of 1. Therefore, it is so rare that Fn takes only O of x power epsilon values in 1 to x, because it takes the same values again and again, but we don't include the details here, and therefore that's a statement which they made and they stopped there, and that's exactly what I want to look at. Therefore, the question which you want to know is how many values fx will be taking, and there is type of result which you want to prove is the number of values which fx will take would be less than exponential constant times square root log x by log x. That's the type of number of values which you will take. That's the question which we have. Okay. Therefore, first of all, let's make some observations. If you take an nth power, you make some observations. How many ways p1, p2, etc. pr can be written as product of integers distinct bigger than 1? Okay. And this number is closely related to what is called the Bell number in combinatorics, which most of you would have seen. Okay. And the second question is, what happens to an nth power? Then writing p power n as product is same as p power a into p power b into p power c, which is same as writing n as equal to a plus b plus c, which is the same as the partition function of the power. And for that's what we get. F of q power n equal to p power n, and f of p1, p2, etc. pr equal to br. Okay, this is exactly what it is. And now how are we going to compute this fx, and how are we going to say how many values does it take? And as usual, one takes a generating function. Therefore, what you essentially have is a so-called generating function, a vector generating function. Okay, therefore, let me just explain what is this vector generating function which I am taking. You see, what I did earlier, n is equal to some x1 plus x2 plus etc. xr. This is the type of partitions which I was looking at. Okay. But now instead of looking at these partitions, we can actually generalize to the higher dimension. Therefore, you can ask the question, how many ways n1, n2, n3 can be written as x1, y1, z1 plus x2, y2, z2 plus x3, y3, z3 plus etc. Here, therefore, x1 can still be 0, y1 can be 0 and z1 not equal to 0. Now, that is the type of things which you are looking at, and that is exactly what you are looking at, and this is exactly the generalization of the ordinary partition to higher dimension. And finally, the question really boils down to how many ways this can be done, because that is exactly the question which you are asking, essentially, because suppose you are looking at the number p1 power n1, p2 power n2, p3 power n3, and then you are interested in knowing how many ways it can be factorized. The question, therefore, how many ways p1 power n1, p2 power n2, p3 power n3 can be factorized is the same as in how many ways n1, n2, n3 can be written as an additive partition with not all coefficient is 0, which essentially means that you end up with saying obviously, therefore, the generating function is precisely going to be, therefore, earlier the generating function for x power n1, this was a generating function. Now, in this two dimensional, it will be the generating function will be something like therefore, that is the type of function which you have to study. Therefore, the type of function which you have to study is the generalization of what we did for the partition function, which is 1 minus x inverse. Instead of that, you get 1 minus x1 power n1, x2 power n2 inverse, and then you want to know this is the coefficients of fn, and then you want to know how many fn's are there, distinct values of fn's are obtained. And therefore, I need to know something about the coefficients, and the something about these coefficients is somehow related essentially to therefore, the coefficient is essentially related to this. Therefore, I can write the coefficient explicitly. I can write the coefficient explicitly. It is 1 over e times 1 over k plus 1 factor, not explicit, at least the lower bound I can write explicitly, 1 over k plus 1 factorial into product k plus alpha I choose k. Therefore, these are the type of coefficients, and now finally, therefore, it boils down to studying the order of certain binomial coefficients. And the way to study the binomial coefficient is essentially to study something called the gamma function, okay, which is the important functions which will come in all these things. And how many of you have studied gamma functions and the so-called formula, which is something which you will be doing actually even in these engineering things. Okay, therefore, let me just explain what these gamma functions which will come in all these things, and then I will stop there. Gamma function is the so-called one of the special functions which is essentially determined by this integral. Therefore, the gamma function is this integral 0 to infinity e power minus t power s minus 1 dt. Okay? And what is interesting in this integral? The most interesting part of this integral is essentially when you look at gamma n, and that would be essentially n minus 1 factorial. Okay. Therefore, let us put this question slightly differently. Therefore, I have a function which is defined only on integers, and I have no natural way of extending the definition to real numbers, is there some natural way of extending that to real numbers? That is a question which Euler asked, and the particular question which he took is n factorial. Therefore, I have a function which is defined as n minus 1 factorial on every integer, okay. But then there is no way I can define what is 2.3 factorial, no. I mean, of course, if you know 7 factorial, this can be easily defined. But on the other hand, if I want to know something like a 2.3 factorial, this of course makes no sense. Good. Therefore, the question which you want to know is there a nice C infinity function, nice continuous function, which would coincide with the n factorial on the integers, but on the other hand, which is defined for all real numbers. And then he came up with this function, gamma s, which is 0 to infinity e power minus t power s minus 1 dt, and therefore this would give you a value for on gamma n that will be exactly n factorial. And this is first of all useful, at least in one sense, for the sense in which we are trying to do is, suppose I am now interested in knowing again the same old question, how fast the n factorial grows. Then if you want to know how fast the n factorial grows, again it is very difficult to know exactly what is going on, but on the other hand, by looking at this as an integral whose things can be easily studied, it can be proved, which is so called the Stirling's formula, which says essentially gamma n is equal to n power n minus half e power minus n square root of pi. Okay. Therefore, this already gives you an idea how the n factorial grows. For example, if you want to compare n factorial with the n power n, it is very clear that n factorial has to be less than n power n, because n power n is a product of n elements all equal to n, whereas n factorial is a product of n elements 1, 2, 3 etc. equal to n. But suppose how much they will differ, how much the n factorial will differ by n power n, and this formula says essentially it will differ essentially by only a e power minus root n. Okay. Therefore, in fact, that means n factorial is really very close to n over e power n. That is what this formula says. Therefore, this gives you a roughly an idea about the growth of n factorial. And these growths of these various functions found by these generating functions is exactly what one needs to study the problems of these types. And then I think I will stop there.
Thank you so much, sir. So, do anyone of you have any questions?
Yeah.
Yeah. I was taught gamma functions in 12th standard. Hi. Yeah. I was taught gamma functions in 12th standard, but I never could figure out how you can get from factorials to that. I mean, is there some obvious way to see why n factorial is related to that integral? Or
Yeah. That's sort of okay. That's essentially integration by parts, and nothing more than that. You see, you have what? E power minus t. Okay, what is gamma n? Gamma n is equal to 0 to minus infinity e power minus t power n minus 1 dt. Correct?
so just integrate by parts.
Exactly. Now you take it as 0 to infinity t power n minus 1 d of e power minus t, and there is a negative sign, because d of e power minus t will be e power minus t with a negative sign. And now you can integrate by parts. Okay, at infinity this vanishes, at 0 also this vanishes. Okay, there will be a negative sign again, because there is already a negative sign. And what is this thing? This is nothing but n minus 1 into e power minus t into t power n minus 2 dt. E power minus t power n minus 2 dt is gamma n minus 1. That's all.
Got it.
Over. Then n minus 1 gamma n minus 1 n minus 1 into n minus 2 into gamma n minus 2 blah blah.
Any more questions?
Yeah.
Do you extension to finite groups? What's the number of representations of an element, either in terms of how a group element can you partition into
An expert is sitting here. I will leave it at that.
Okay.
My personal feeling is more or less for an abelian group it is so easy not to be an interesting problem, and for a non-abelian group it is so difficult not to be an interesting problem. Isn't it?
Yes, something like that.
Yes.
One more. This hypergeometric series, of course, come as solutions of differential equation.
Yeah.
How can use the differential equations?
Yeah, but he has to. Yeah.
No.
Yeah, but to study the. Yeah, I think in fact the original motivation of even Gauss to introduce the hypergeometric series is really he wanted to study the solutions of differential equations, and but then it has gone in so many other different ways. He is there to do all the Ramanujan things, hypergeometric functions. But I don't think Ramanujan ever used the hypergeometric functions as a solution of certain differential equations or anything like that. Yeah. Yeah. Exactly. Yeah.
These operators are the Ramanujan operators.
Ah.
Some differential equation, right?
That is true. Oh, particularly for P, Q and R.
That's right.
Which is used by Nestor and Co. very much for transcendental number. Yeah. But that is due, no, for modular forms, etc. he has done left and right. But hypergeometric series as differentially, as per se, I don't think he has studied as a differential equation.
They will come up in geometry and this, what do you call it? Monodromic.
Yes.
So there it comes as solution because you want to look at regular singular points and then solutions. So when you see from the algebraic geometry, action.
Some differential geometry point of view, because this connection is very important.
Very important.
Very
And then
important.
it comes this thing. So like
Exactly.
some of these people seem to have had that kind of intuition.
Yes, exactly. Yes.